Since the energy in an electrostatic field is proportional to the square of the charge that creates it, its spatial distribution does not depend on the sign of the charge, as it does with the electric potential. Because to positively charge an object, electrons must be extracted and added if negatively charged, I considered the possibility of assigning a sign to the field's energy density. Continuing the comparison with electric potential, the logical step would have been to assign a positive sign to the field generated by the electron extraction. At that moment, I remembered that before knowing that electrons were current carriers, it was assumed that positive charges moved. If the true carrier's nature had been known, the electric potential signs likely would have been reversed. Considering that these signs by convention were defined, I looked for a more intuitive analogy. That is how the comparison with containers filled with water arose. We saw that the work done to extract water from a container decreases its level while the water level in the container where it is deposited increases. This analogy led me to suppose that electron energy increases when extracted from an atom, and the resulting ion energy decreases in the same proportion. Therefore, I propose that the field energy associated with negative charges has a positive sign, and a negative sign corresponds to positive charges energy. This involves considering a zero energy level, corresponding to regions where the field is extremely weak. From there, depending on the sign, there would be energy levels above or below zero. Finally, instead of talking about electromagnetic pulses, I began to imagine quanta of energy, or photons, continuously emitted by the charged object as a consequence of its temperature. But this brought with it a new complication. If the object continuously emits photons, it loses energy and cools. To maintain its thermal equilibrium, it must receive the same amount of energy from its surroundings as it emits. Perhaps a simpler and more realistic explanation, more closely related to the physical processes we already know, lies in something we constantly observe and measure: thermal energy and its radiation.